He got affected by the Press committee. Water. Because it's getting a bit late. So it's actually, I welcome all of you again for this week's Wednesday colloquium. And it's really a pleasure to have a very close friend, Professor Ayan Datta, come to us from ISES Kolkata. Just for everybody's sake, and Ayan's sake as well. The colloquium series is pretty traditional to TIFR, Ayan. It was started by Professor Homi Bhabha's time, and just because at that time, because he was so busy, one day he used to visit for the whole of Wednesday to TIFR. And during that time, this colloquium would be organized because he would be part of a seminar where the discourse would be to include everybody in the institute and have an expert, eminent expert, talk about any topic in physics, chemistry, and biology. So this is a age-old tradition, and we've been lucky to maintain it. So coming back to Professor Ayan Datta, so Ayan actually did his bachelor's from Ramakrishna Mission Rohira College, and this was from 1998 to 2001. Because he was a very smart student, JNC ASR in Bangalore picked him up for an integrated PhD program, something that we also do in certain cases, this integrated PhD program for almost 6 years, that involved him to go to JNCSR and pick up theory as a major sort of direction in chemistry. And he worked with Professor Shapunpati for both his master's and PhD, finished his PhD in 2007. And then he went to University of North Texas for a postdoctoral stint for almost a year before he was called back again to be part of a young institute, which is ISER Trivandrum, something that Kalaivanan also remembers because Kalaivanan was a graduate student at that time when Professor Datta was a faculty there. He moved from ISER Trivandrum in 2012 and has been with ISES for the entirety of time. One of the important aspects of Ayan's research has been that he has picked up problems which are creative, but also yet very simply dealt with. And some of the very creative work has led to some, discovery of different kinds of alloys that can have very nice properties. Especially his work on long CC bonds, which he coined the word ultra long, has been a very important topic in recent times. Also, he has been working on, developing simple models to treat things like photoexcited processes like singlet fission, some of the work we've done together. And of course, his work has also involved colleagues here, Vivek, for example, his work with Vivek in catalysis. And so it's a very large spanning work that has involved using methods which would, so that the time problem in calculation is under control. He has used simple models to describe that, have solved the issue depending on the chemical problem. Because of his very nice work, Ayan, of course, has won many awards, and one of them is the B.M. Birla Science Prize in
So I think
2017
we can.
and the Serb Distinguished Investigator Award. With that, Ayan, I welcome you for the.
Yeah. So this time is not included in my discourse.
Okay. Okay.
So I'm going to remove this. So I'm going to set the zero from here. Okay. So first of all, let me start by thanking Jyotishman for this wonderful and kind invitation. And I am also thankful to my friends here, and of course, Vivek and other friends, many here, and some of the very young chemistry colleagues whom I met. In fact, I listened to them, I interacted with them for the first time. I met two, three young faculty members, and so of course we have a wonderful thing here. And of course, my very good friend Pratap, more of a Facebook friend, more with me, with I interact with him, and it is such a wonderful place to be here. And if you think of the density of creativity, probably in India it is highest in this place. I mean, if you look at the density of states of creative minds, I would say in this place would be probably highest than anything else. So if you think of the pinnacle of educational creativity, I would say TIFR means it. And it meets it in its whole full glory in its all sense. And thank you very much for the very kind information. It really means a lot. I mean, it's not easy to be get invited in TIFR. I understand that. Okay, so I'm going to talk to you about something which are like buckling and defects. Now, whenever we talk about defects, is something it's like taking the sheen out about the creative excellence of something. So whenever we think whenever we think of beauty or appreciation, we think that is something which is pristine and something very clean, no distortions, no dag, I would say. But probably at the end of the next 50 minutes or so, I will try to convince you that it is the buckling and defects which actually gives a lot of interesting physics and chemistry to materials. And it also gives a lot of things which probably gives us a handle as a chemist to look at those states. Of course, we don't need to, at least here, I don't need to talk about this slide, just to give the things in a little more perspective. When we talk about two-dimensional materials like graphene or graphite, we mean something like you have, if you think of a molecule like benzene, and then you can think of a molecule benzene, and then if you're able to fuse benzene rings together. Now, what will a chemist do? He will take a benzene, he will fuse two benzene rings together to make naphthalene. He will fuse three benzene rings. Now, when you fuse three benzene rings, you have options. One, if you fuse them linearly, you will get anthracene, whereas if you fuse them non-linearly, you get phenanthrene. Both the molecules are known in a chemist. Now, think of the hypothetical question that I am able to fuse lots and lots of benzene rings together to make a very large aromatic surface of hexagons. Well, what will the chemist call it? Chemist will call it polyaromatic hydrocarbons. Polyaromatic hydrocarbons. There are a lot of hydrocarbons together. Whereas, if you're looking the things from a top-down approach, you would probably call them as mimics of graphene-like systems. Now, both the approaches have been tried in different ways. Now, I must say that the bottom-up approach in which you could fuse, you could tie things like a stitching of your knitting of a sweater, people have tried to do that. For example, Klaus Muller has been able to make molecules. I mean, these are like world records for chemists. Like you could fuse 200 such benzene rings together in a linear fashion to get something very large graphene-like fragments. Typically, however, if you really want to make graphene, you typically make graphene by take graphite and then you peel off layers like using a scotch tape. Now, it is easier said than done. It is not easy to peel off a single layer. You need a lot of calibration and experimental hand to do that. But then, and typically you do that and you calibrate them by the most famous work of my institute, which is doing Raman. And then you do Raman to find out whether the D and the G bands are making some sense. Now, so about 15 years back, we started by asking a question. We asked the question whenever we talk about two-dimensional system, we always talk about graphene, carbon-based system. So what stops us from having something called inorganic analogues of graphene, something like silicene? Now, what do you mean by silicene is you have a silicon which is fused just like graphene. Now, this was a question which we wanted to ask, and then subsequently we also went ahead and we looked at other inorganic or other analogues of graphene and to see whether you have the same kind of properties like this. Now, I must say, when we have graphene, you have an isoelectronic equivalent of graphene, which has properties which are very, very different from graphene, and which is called hexagonal boron nitride. Hexagonal boron nitride is isoelectronic like graphene. It is isoelectronic because boron is 1 electron short of carbon, whereas nitrogen is 1 electron more of that of carbon. So if you have hexagonal boron nitride, you add up all the electrons fine, but because of the local change of the local bond moments in different direction, hexagonal boron nitride is a hopelessly band gap material. So hexagonal boron nitride is good and it is a perfectly planar system, but then we wanted to ask question whether we have an isotropic monoatomic subsystem and then whether we can have graphite-like properties out of it. Easier said than done because of the fact that if you go from sigma to pi orbitals, I mean, if you go from carbon to silicon, the story changes. And this story has been a very long story in chemistry. See, one of the very initial calculation methods were using like the so-called Huckel theories, which nobody uses anymore. Something like as rudimentary as tight binding methods, where people were only looking at the pi orbitals. But then people soon figure out that it is the pi orbitals alone are not enough to give the whole picture, because you need to worry about the sigma electrons as well. So the fact that as you go from carbon to silicon, or for that matter, the sigma and pi orbitals start talking to each other. They have now started coming closer. As a result, it is not physically possible to separate the sigma and pi separately. As a result, they talk to each other and end up mixing. So that is a story which has been an issue. Now, we were not the first person to ask the question. I mean, to the best of my knowledge, this is a work from Japan, Shiriashi, and the title of the paper in Physical Review says theoretical possibility of stage corrugated silicon and germanium analogues of graphite. This is a paper by them, and I can bet 100 rupees and tell that nobody will write a title like this anymore. The reason why nobody will like this title anymore is because, of course, they were talking about a single monolayer of graphite, which we call today as graphene. But remember, this is 1994, so this is also a kind of a good tutorial for how to write a title of a manuscript. So the title of the manuscript also represents the state of the art at that moment of time. So today, if somebody will write a title of this paper with the same result, people will write the same thing: theoretical possibility of stage corrugated silicon and germanium analogues of graphene. Because now we know that you could peel off one layer of graphene from graphite. But this is 1994. Novoselov and Geim has not taught us how you can probably take out a few layers. So then the people ended up writing a paper with graphite. But remember, these are very rudimentary calculations. But the idea was that can you have silicon or germanium analogues of graphite? That was the question which we were asking. But this is a monolayer of this. The field really took off with this paper by Guy Lillet at Marshall, in which, by the way, they are surface physicists. And with this article in Physical Review Letters in 2012, where they found out that if you have a silicon monolayer, that has a graphene-like properties. So it has a Dirac cone-like properties, which is a good enough understanding that probably it has graphene-like structure. I must add a caveat here that these experiments have been subsequently challenged. The reason why these experiments have been challenged is because of the fact it is the experimental limitation of the phenomenon. See, what happens when you try to make a monolayer of silicon is extremely susceptible to atmospheric oxidation. So what they did in this experiment, they had a layer, I mean, they had a surface of gold 111, and they figured out that a gold 11 layer or gold 110 layer, depending on the lattice matching, they were able to deposit a monolayer of silicon over it. Now, when you actually measure, you take an STM tip or something, when you measure its current, you are not very sure what current you are measuring from. Are you measuring the current from the top silicon layer, or you are unfortunately measuring the current from the background metal surface? So people have figured out that probably they were measuring the current from the metal substrate at the bottom, and of course, the state had a mixing with the underlying surface. So the experimental challenge in getting a monolayer silicene, or for that matter germanene, is to be able to deposit a monolayer of silicon or a monolayer of germanium or a monolayer of any metal over an insulating surface like hexagonal boron nitride. So if you have something like hexagon, if you have an insulating surface like hexagonal boron nitride, then you know for sure that surface state, that surface, that one monolayer, that electrical conductivity or that density of states is the one which you are measuring. So that is still an open problem in an experimental sense. Now, I gave you a picture because this is a TIFR is a very unique place because you have a very high, I mean, blend of both physics and chemistry, and actually more physics. And then, so I think, look at the way in which this subject has evolved. Now, this is, I give you an example from the top-up approach. Now, chemists were also interested to address this problem. Now, what would a chemist do? A chemist will do exactly the opposite. Chemist will take a molecule and try to replace the carbon by silicon. That's what a chemist will do, right? So what the chemists were doing, I don't know whether you can see it. This molecule is naphthalene. Where do you use naphthalenes for, the young people? Well, nowadays we don't use it for. Naphthalenes were the old technology, you know, when you have moth, when you have clothes. I mean, of course, the young generation doesn't want to wear old clothes. They will anyway throw the older ones. But anyway, people like us, we would still be wearing the old clothes, and we will put naphthalene balls to the almirah. So when you open the almirah, you will have that smell of naphthalene. But believe me, you guys are smarter. Those are all these naphthalene or polyaromatic hydrocarbons are tremendously cancerous materials. So we should not be using it. You're right not to use it. Okay. So don't be apologetic of not using old technologies. The reason, in fact, in Western countries, using naphthalene balls is completely prohibited. They're all notoriously carcinogenic. But then this is naphthalene. Just to give you, this was just a caveat. So this is naphthalene. What these gentlemen in Japan they were doing, they substituted one carbon and put a silicon here. Similarly, this is even more. This is benzene, and they substituted one carbon by silicon. There are two observations we can see from here. The first is when you replace one carbon by silicon, the structure has still remained planar. So in other words, you could replace at least one carbon by silicon and still see that the ring is planar. So in other words, if you replace graphene and put one silicon inside, probably the planarity will still be maintained. It will not be buckled. However, being experimentalist, what you need to do, you need to put a very big bulky group around that ring. Why do you need to put a very bulky group? The reason why you need to put a bulky group, because remember, chemists are working under oxygen and water. So under oxygen and water, a carbon silicon bond is extremely susceptible towards oxidation. So of course, this molecule has to be protected. These are what are called protecting strategies for an organic chemist. So you have to protect this so that the carbon and silicon bond does not get oxidized. I hope I'm able to tell you that. So now the question here is the fact that you could replace a carbon by silicon and still see that the ring has not puckered can have the origin of this can have two reasons. One, that yes, in principle, you could replace a carbon by silicon and maintain its planarity. Probably it has to do with the chemistry of the thing, or otherwise it is the hypothetical fact that you have to put a very big bulky group to protect it. Maybe the bulky group is doing that. Now, this is a wonderful question for a theoretician to answer, because the only thing which a theoretician likes is not to have bulky group, because you want to do calculations on simple systems. So now this is exactly the toy calculation which we did. What we did is that this is benzene. By the way, this is 2010. I can promise here in 2025, if you write this, if you do this work and publish this paper, nobody in the world will ever be willing to publish this, because this is too trivial. You can do it on your forget laptop. You can do it on your mobile. Even maybe ChatGPT can give answer to this. No, the point which I'm trying to tell you here is this is 2010. And in 15 years back, this was a viable, important question to address. But then, whatever important, viable questions are there about 14 years back are no longer relevant here. So it is very important to scale up your questions and scale up your level of difficulty. It is very important to do that, to remain state of the art. So that is one point which I wanted to make. The other thing is, so when we did those calculations, and those calculations were substantial at that point of time, is when you replace carbon by silicon, and you see that you could replace one carbon by silicon and the system remains planar, exactly what we had seen from the crystal structure. And when we replace all the carbons by silicon, the structure has buckled. So this was a prediction which we made. This was 2010. Okay, this was the prediction, very simple prediction. And gratifying, in the same year, Seskevich reported this article in Science saying that exactly, They're saying exactly that he has made hexacillabenzene in which you have replaced all the carbons by silicon, and you could see that the structure is puckered. Exactly what we predicted. Yes. Oh, no, this is because, experimentally, it is very difficult to make selective ones. So hexacillabenzene is probably a better candidate to be synthesized. It was also, remember, the reason why it was in science is because this was one of the experimental challenges in that decade to make a molecule in which all the carbon atoms in benzenes have been replaced by silicon. This was an experimental challenge which was taken up this. It was very difficult to make this molecule. And you see, it was difficult because you have to again protect this with very bulky groups. But the point is, even without protection, when we do those toy calculations, the structure had bent. So the fact that you could yeah.
When you have all the six and still
Yeah,
it's a symmetric model.
no, but the 5 carbon is still not been made. Nobody has made it.
No, theoretically.
Yes, it's bent. It is bent. It's puckered. So more than 3 of them, the structure is puckered. So I would say that even now, some of these predictions have not been realized. The 6th one is still, it was a challenge at that moment, but people did make it. So the 6th one, the reason why it is 6, because 6th one is the molecular analog of what we call as silicene. That is the point we made, because you have replaced all the carbons, and if you are able to think of it in the 2-dimensional space, this would be equivalent to that of silicene. Now, the point which I'm trying to make here is, in other words, if you have a perfectly planar hexagonal structure of silicon, that will be vibrationally unstable, and when it buckles, it will be vibrationally stable. I will come back to this weird looking phonon spectrum. It may not make sense directly. I will come back and I will tell you how does it matter. Now, when we talk about phonon spectrums in solids, this is actually, we are looking at the normal modes, but then we are not only, but molecules do not have, molecules as such will not have those translational symmetries. But then when you have a solid, you will have translational symmetries. So you will have, apart from that, what we call at the gamma point, you will also have other symmetries which are coming from the periodicity of the system. So the fact that if a system is vibrationally stable, that will not have any imaginary mode. Why do we call imaginary mode? Something which has imaginary mode, if you have the stretching frequency, you remember the stretching frequency is, at least for a harmonic approximation, goes as the square root of the force constant. And if the force constant is negative, which means your system is not stable, but the system is a saddle point. So the force constant is negative. In other words, any particle which is sitting on the top of a saddle point will roll off. So the force constant is not restorative, but distortive. In fact, at that moment of time, we also did some toy calculations in which we found that if you had metal ions on the top and bottom of those silicene monolayers, the structure again regains its planarity. In other words, if you have a distorted silicene layer, monolayer, and if you have metal atoms on the top and bottom, you again regain its planarity. Now, we did these toy calculations with lithium, and I must say, Jyotishman, that we were not particularly interested about lithium. Other than, lithium has very important role. All our batteries are filled up with lithium-ion batteries. But apart from the fact that we were not schizophrenic about lithium, right? Yeah. But the point is, the reason why we were only interested about lithium, because the reason why I said schizophrenic, because if you are very unfortunate, you have to take lots and lots of lithium. Very sad, but then that is probably, very rudimentary medicine, but that is the only medicine we have. Okay. So now the point is, the reason why we did it on lithium is because, again, we hate big systems, because doing calculations on anything which has more number of electrons was difficult at that moment of time. So we had predicted with lithium, had we known, and maybe had I talked to Vivek, maybe at that time I did not know Vivek. Well, Vivek would have told me, why are you looking at lithium? There are inorganic phases of materials like calcium silicide. This is a phase of calcium silicide in which there is a perfectly planar. By the way, these are what we call now are like Van der Waal-like materials. It's like they are monolayers of silicenes in which there is calcium which are intercalated between the layers. And you see for the crystal structure yourself that the structure is perfectly planar. So the fact that if you have metal atoms or metal ions, you can call them both because it doesn't matter. The calcium would anyway give up its own electrons. The structure regains its planarity. So now we have to explain two phenomena. The first phenomena is you replace carbon by silicon. structure has got distorted. The other phenomena is if you have the distorted structure and if you have metal ions on the top of it, the structure will regain its planarity. I hope I have been able to make those two questions clear. Go from carbon to silicon, the structure has buckled, and now even that buckled structure will regain its planarity when you have metal ions on the top of it. How do we explain this? So that was the question which we had. And for this, we go back to a very, very old theory. And this is the theory, by the way, this theory has been extensively used in the world of ferroelectricity. So this is what is called the displacive phase transition phenomena. So what is happening here? Consider the fact that you have a ground state and an excited state. For that matter, any molecule, any material would have multiple excited states. Now, consider this toy model of a ground state and excited state. Now, because of vibronic coupling or electron-phonon coupling, the ground state and the excited states would mix. And because of the mixing, two phenomena happens. The ground state actually becomes more and more relaxed, whereas the excited state becomes more and more rigid. And why does it happen? It is a very simple second order mixing perturbation between the ground state and excited state. So this is the non-degenerate perturbation theory. Because of the mixing between two electronic states, the ground state gets destabilized, the excited state gets the ground state gets stabilized, the excited state gets destabilized. Now, this is known from 1940s. Herzberg, when he was looking at the structure of benzene, found out that for the excited, when you excite benzene to its second excited state, he found that the CC stretching frequencies actually became rigid by 300 wave numbers. Whereas the ground state, because of this mixing, actually becomes more and more relaxed. And eventually, in the limit of instability, this would develop an instability. In other words, what was stable at this point has now become destabilized, and it will reduce its symmetry to get a double meaning.
And just one thing, I just want to clarify that it will depend on the energy gap.
Of course.
So the energy gap, with that large energy gap, maybe it's a small effect, but when it comes closer and closer, you will see that.
Yeah,
effect,
but
right?
but I am supposed to give the conclusion for the talk because you are giving the you understood and you understood exactly what is going to mean. Yeah. Thank. I understood that you are a very bright person, so you understood what I'm going to tell you. Yeah, that's okay. That's absolutely right. So the point is, in fact, some of you, if you are interested, this problem, by the way, it is the same problem which governs superconductivity, or at least in the BCS-like superconductivity, in which people also worry about vibronic interactions. Because and people have done this kind of lot of calculations for materials in which people have tried to control the vibronic interaction. Because it is the vibronic interactions between those states which control the superconducting TC. That is the order parameter which people think of. Now, the point is, how strong is the mixing? If the mixing is strong, the ground state will develop instability. And because of the instability, it will reduce its symmetry and break off and come out of the symmetry. And this is the fundamental theory of what we call as second order Jahn-Teller distortion. Why we call it second order? First order is where the ground state is degenerate, or the normal Jahn-Teller. When we say Jahn-Teller, for example, the very famous examples are those D9 systems, which are degenerate. Now, if the states are non-degenerate but close by enough to destabilize each other or vibronically couple with each other, even they can perturb, and this is called second order Jahn-Teller distortion. In fact, the second order Jahn-Teller distortion is probably the reason we can probably explain the arise of why you have ferroelectricity in barium titanate. So the titanium is not sitting exactly at the center of the octahedra, but it is moving up or down. The reason why it moves up and down is because of the mixing between the excited states. That is one of the. I mean, this is a very old theory. I mean, very strong theory. But then that theory has I will come back to it and to explain. We have been able to use this to explain this. So now what is happening here? This is, by the way, don't look at the numbers as such because these numbers are for molecules. So molecules are hypothetical. When we go to materials, of course, because of the band gap effects, the band gaps are going to come close, so vibronic interactions are going to be larger. But the proof of principle is when you go from carbon to silicon, as you go down the group, as you go from carbon to silicon, your electronic states are coming closer. Why they're coming closer? Because as you go from carbon to silicon to germanium, things are becoming metallic. So electronic states are coming closer, and if they're coming closer, they can vibronically interact stronger with each other. And because of vibronic coupling, they're going to have destabilization. Now, what happens when you have metal ions? Well, what metal ions do is just they create charge transfer between the state, and because of charge transfer, now the gaps have again opened up. And if the gaps have opened up, then these guys do not interact that well. As a result, the vibrational instability is gone. There is a very typical toy way of looking at it. That's what we did. Now, yes. Oh, LUMO plus is to find out those electronic states which have the right symmetry. See, because by the rules of normal modes, only those modes which can vibronically couple with the ground state should have the total symmetric product of the state. For example, if your ground state is Ag, I mean, it's just a Ag, then your excited state also need to be B2G for that matter, to have a totally symmetric product. These are the vibronic selection rules. Now the question is, well, then why the chemist's favorite molecule, benzene, is not puckered? The reason why benzene is not puckered, because it is true, benzene also has this distortive an electronic state which can in principle interact with that, but that is at 8 electron volt, much higher in energy. So if it is higher in energy, even though they interact, they are not enough to create this instability. Whereas when you go to silicene, for that matter, the gaps have come closer. It has gone from 8 to 3, and for that matter, even closer. Then, of course, they can couple stronger, and because of this, it has developed a double minimum. So the point which I'm trying to tell here is that very likely as you go from carbon to silicon to, for that matter, other materials, as you go down the group, you will have more and more distortive-like pictures. That is what we wanted to predict. So at that moment of time, we actually computed the vibronic coupling constants. And what we did, so you see, if the square of the force vibronic coupling constant divided by the gap, so if the gap is less and the vibronic coupling constant is high, then of course this term will become, this is anyway negative. So this term will overrule these interactions, and because of this, the force constant will become negative. And if the force constant becomes negative, what happens to the stretching frequency? It becomes imaginary. And if it's imaginary, then of course it will see the rule of the game. If a molecule or material has to be stable, all the force constants have to be positive. In other words, if you push that that molecule or material out of that structure, it will come back to its structure. It's like this: you are at a pendulum, and this is the mean position. If you push it here, it will come back here. But then, if the pendulum is not restorative, then if you push it, it will fall off. That is the point between an attractive and this thing. So what we predicted, was that if you have silicene, that is going to be distorted. This was known. We also predicted at that moment of time in 2014, germanene was not known. So we said that, yes, I'll just come. So what we said, that if germanene is made, if a monolayer germanene is made, it is also going to be puckered just by looking at that number. Yes. Yeah.
Go down the group, basically. See, is the coupling increases or the energy gap between
it's a very good question. I would tell you the easy answer. The easy answer is gaps are easy to understand. So of course, if nothing else is, if vibronic, even if you address, there are two things. So vibronic coupling constants increase, or even if the vibronic coupling constants remain the same, since the gap is decreasing, that is enough to create the distortions. The answer is, the reason why I give you this simple answer is because calculating those vibronic coupling constants for materials is not that easy. So even if I am not able to calculate it, even by looking at this, I can tell this. Very good question. Thank you. Wonderful. So what we said in 2014, that unlike graphene, if you have silicene, that is going to be distorted. So silicene structure is a distorted structure. And gratifying for us, because there were subsequent to this, there was a very, very large number of two-dimensional systems like germanenes, experimentalists reported, and you see, they all reported buckled germanene on platinum surfaces and so on. So what we said, that germanene, we had predicted that germanene is going to be distorted, and gratifying for us that germanene was indeed distorted. Incidentally, this is 2014 and 15. There was a large, in fact, we had a new material which was called phosphorene. Now, what is phosphorene? It is two-dimensional phosphorus. So two-dimensional phosphorus is the only other two-dimensional material which you can peel off, just like exfoliation, and it has a natural band gap. For example, graphene, unfortunately, does not have a band gap. So as a result, people have to do a lot of tricks to open the band gap. Whereas phosphorene has a natural direct band gap of about 1.5 electron volt, which is very, very good. You want to make materials in that region. So there was a lot of subsequently now about there are 30,000 papers which have been written on two-dimensional phosphorus, which is called phosphorene. So what we predicted is that if you have two-dimensional phosphorus, that two-dimensional phosphorus. Now, incidentally, if you look at the various allotropes of phosphorus, there are various allotropes of phosphorus. For example, the one of phosphorus which we use in Diwali is this the phosphorus tetrahedra which you use in Diwali for getting the fireworks. Whereas, interestingly, there are two phases of phosphorus. One is called black phosphorus and blue phosphorus. So black phosphorus is distorted, and it is also a van der Waals material. Whereas blue phosphorus is also distorted, and it is also a van der Waals material. Both the phases are known. Problem between black and blue are both of them are distorted, but the distortion modes are different. Look at the structure of black phosphorus. This is like a stapler clip-like structure, whereas blue phosphorus is distorted like silicene. Now, if whatever I have told you for the last 40 minutes is true, in that case, the fact that you have both black phosphorus and blue phosphorus experimentally known, and then in that case, both black and blue phosphorus should have its common origin from this hypothetical perfectly planar phosphorus, and because of vibronic coupling, you should be able to get both black phosphorus and blue phosphorus. In other words, till now when I gave you an example of silicene, I said that you have one vibrational mode which reduces symmetry and goes to the distorted silicene. Now this is a more difficult problem because now you have two different phases of phosphorus, and those two different phases of phosphorus should start from a single origin and should lead to two different products. Now, how do we understand this? Well, I give you this example. If you are sitting on the top of a horse, and how do you sit on the top of a horse? Using a saddle, right? If you're sitting on the saddle, and if you put a drop of water on it, from the water, it can only fall off either of the two ways, either this way or this way. In other words, if you have a symmetry or spontaneous symmetry breaking from the top of a saddle, the water can fall off only in two ways. Now, think of something more complicated. Now you are sitting on the top of Mount Everest. Now, Everest is a hilltop. Now, if you are on the hilltop, well, yes, if you fall around, if the one drop of ice melts from the hilltop, you can come this way. But remember, it is a hilltop. So perpendicular to the hilltop, there is also one more path which falls off. In other words, if I am on the top of a hill, there are two multiple ways in which I can go. One along this pathway, the other is along this pathway. And this is exactly what we predicted, that if you have, for phosphorus, there are two different vibrational modes of frequency. In other words, the planar structure is not a saddle point, but a hilltop. Now, what do you mean by a hilltop? A hilltop means it is a second order saddle point. That's what we mean on the top of a hill. I'm just giving a simple, I'm a chemist, I understand things in a very simple fashion. Yeah, yes, it can give many. I told at least more than one. Okay, so this is not that complicated hilltop. I have not been able to find a material where you can have more than one. I'm looking for it. You're absolutely right. In hilltop, you have a very large number of possibilities. Ideally, maybe the answer lies here, because for the complicated materials, probably you can go from one symmetry to another symmetry, and from that another symmetry to another symmetry. So, you increase the phase space. But then this approach of mixing between the ground state and the excited state provides me a uniform, simple handle to understand in a kind of a unified way of looking at it. Of course, chemistry is far too complicated to be made into a single theory. So, what we said, in fact, now the point which I'm trying to make here, this is black phosphorus, whereas this is blue phosphorus. So you see, they are distorted in different ways. Now, the reason why it is called blue is because it is an indirect band gap material. So because it is indirect band gap material, it has very important applications. These are lots and lots of papers have been written on this. I know at least 25,000 papers have been written on this kind of phosphorus materials. Whereas black phosphorus is a direct band gap material. It's a 1.5 electron volt gap material. Now, those who are interested can look at this work by David Tomanek. He has looked at several work, but I give you only two examples of this, just to give a feeling that the topology of those two surfaces are different, and they arise from a possible hypothetical high symmetric structure. So this is the point which I'm trying to tell here. Graphene, if you look at the frequencies of graphene has a gamma 2 frequency, gamma 2 mode, which is real. The reason why graphene has a gamma 2 mode real, I will come back to the next slide, but silicene has a gamma 3 which is distorted, negative. Whereas if you look at other material like phosphorene, phosphorene has multiple bands of instability, and those multiple bands of instability will lead to different structures, not necessarily one via another. Some can be directly and some can be indirectly. In other words, for example, this is exactly what I told you. For graphene, the only way you can probably get an instability is by mixing of the electronic state of this, say maybe say HOMO minus 2 or HOMO minus 2 with this. Now, this is a very large band gap, 10 electron volt. Whereas, as you go to silicene, this is a very small mode interaction between the state. Now, for phosphorene, there are multiple modes and there are multiple mixing between the states. And because of this multiple modes of phonon instability, distortion along the gamma mode produces one structure and distortion along the M mode produces another structure. So, this is the point which I am trying to make is, for example, if you have a blue phosphorus, which is this distorted, it is a single mode of distortion which brings you here. Whereas for black phosphorus, you go to an excited state which is distorted in a different way, and then that undergoes further distortion to give a structure like this. So this would act as an intermediate. Now, this is a small prediction which we are making, that the formation of black phosphorus goes through an instability, intermediate instability wala compound. Now, this is something which I would look somebody to look at experimentally and find out. Now, this is not that people have not looked out. I give you this very famous example in physical organic chemist. Actually, I am trained as a physical organic chemist. So I'll tell you this very famous example in chemistry. You have this molecule called cyclooctatetraene. Cyclooctatetraene, the ground state of cyclooctatetraene is actually tub-shaped structure. But then you can't form the tub-shaped structure from the perfectly planar delocalized structure. So the first happens, the cyclooctatetraene undergoes an in-plane distortion of double bond, single bond, double bond, single bond. In other words, it goes from a 8-fold symmetry to 4-fold symmetry. This is one symmetry breaking. And from the 4-fold symmetry to out-of-plane distortion to the tub-shaped structure. So this is known in chemistry, and this has been verified experimentally by photochemists. But then in the materials, that that has not been explored. Yes, Jyotish.
Yeah. Ayan, so how big a structure you would need for an experiment to do, in the sense this is on an extended material?
Yes.
Or you can clip it? You can clip...
this is a periodic material.
This is a periodic material. So you can do it on a powder, for example.
Yes.
And
by the way, phosphorus, black phosphorus for that matter, is something you can peel off. I mean, it is not as stable as
it's not stable. That's the...
No, but it's stable for a few months at least.
Right. So then you are saying that the first state it goes to is there is an instability there.
Yes, and that state again undergoes
to distortion, another lower symmetry, which is a distorted form.
So if you are able to identify this local minima,
right,
then that is an intermediate to look at.
So maybe the vibrational, you've done the normal mode calculation.
Yes.
So there are certain modes that you can talk about which lead to that.
Yes. Yeah, these are the modes along this mode.
Okay. Yes. Fine. We can discuss. Yeah.
Thank you. Okay. Now, what is the proof of pudding? The proof of pudding is, if there is distortion, the valence band should reduce its energy, whereas the conduction band should increase energy. As a result, there should be gap opening. Then only the ground state will get stabilized. And this is exactly what happens. Now, of course, people have looked at this for other reasons. For example, a black type phosphorus would be an N-type material, whereas blue type will be a P-type material, depending on the nature of it. The reason why, because the extended surfaces are different, so people can use them for different catalytic properties. So what I have not told you here is this problem is that any molecule, material, would have a very large number of excited states. So how many such excited states a ground state can interact with to create the instability? Now we don't want this problem to be intractable. Well, with all due respect to all the best computational physicists, computational chemists of the world, we don't like these problems to become intractable. For example, if for a simple molecule like hexacillabenzene, there are 17 such excited states which have the right symmetry. So I don't want my second order Jahn-Teller matrices to be 18 order things. I mean, these are far too complicated. And of course, they are far too complicated because there can be interactions of all sorts. But then what we did is we removed some of those selective interactions from the Fock matrix. And then we found out that if you could remove some of those selective interactions from the Fock matrix, you could regain the stability. In other words, if you remove those second order natural bond orbital energies from the calculations, and if you see that the structure has regained its planarity, then I know for sure that it is that interaction which was important. And believe me, what was that interaction? Well, the students anyway know the answer. It was sigma pi star orbitals. And of course, it is the sigma pi mixing as you go from carbon to silicon becomes more important. And as a result, exactly what we see, it is because of the sigma pi mixing, these interactions get stabilized. Now, what I also told you is that, see, the fact that you have, as you go from carbon to silicon, distortions become the rule. Now, distortions are also known even within the carbon family. For example, you have distorted carbon structures like T-graphene or trigraphene. So what is T-graphene? T-graphene is like where you have 4-membered rings and 8-membered rings which are fused together. Whereas trigraphene is you have a 3-membered rings and 8-membered rings fused together. Now, what happens here is something very interesting. Now, because of the fact that you do not have all the hexagons here, but you have 3-membered rings and 8-membered rings, or 4-membered rings and 8-membered rings, because of the anisotropy of the holes, they move differently under temperature. So what is happening now is when you heat these systems, now what do you mean by heating? When you vibrationally excite those modes, those individual 4-membered rings move in a different fashion rather than the 8-membered rings. Now what happens if you have those 4-membered rings and if they move in a mode in which the end-to-end distances decrease, then what will happen eventually, your material would appear to shrink rather than increase. Now, this is very interesting because then you will heat up the material and the material will contract. Now, this is a little counterintuitive, I would say. Typically, when you heat a material, it expands. Well, the reason why we think of things expanding when you heat is because of the inherent problem that we consider chemistry as only bonds. Remember, chemistry is not only bonds. Chemistry is also about angles and dihedras. Now, what happens if you heat something and if they get vibrationally, for example, consider a very famous molecule like metal oxygen metal bond. If you vibrationally assist and if you heat it and if it gets populated to a mode like this, so if you heat something and if it gets excited to a mode like this, and if this is the mode which is important, then you will see when you heat, you will either get this structure or get that structure. You see, and if you measure my end-to-end distances with respect to this, my end-to-end distances are actually reduced. Now this, in the community of this kind of networked solids, are called the rigid unit modes. In other words, when you heat something or when you go to the population, those individual modes which are behaving as rigid and they are moving with respect to each other. So that when the tetrahedras are moving, you will see a crumbling motion. So these kind of materials are called negative thermal expansion material. Where do you use it? Well, the young people will not realize, but believe me, for people like us, we certainly feel it now. So I will tell you this. In Bombay, you will never realize this. That is the first thing, because Bombay has a very uniform temperature. But if you go to Mahabaleshwar, or if you go to Kashmir or sometime, so what you happen when you drink something very hot or very cold, you find tooth pain. The reason why you find tooth pain is because people, if you have a capping on your tooth, the material which is used for capping would have a thermal expansion coefficient different from your original bone mineral, the original mineral which nature has made. So what happens, your capping material expands and contracts at a different rate than your natural material. So in other words, there is a lot of interest to make tooth fillers which are of the right thermal expansion coefficient as your original tooth. Now, believe me, if you go to do a tooth filling or when you do a root canal and then they give a cap, an artificial cap on your tooth, the doctor says, first of all, I mean, professors at TIFR, they will anyway figure out that you guys are damn rich. So they will say, no questions asked. We'll give you the zirconia cap. What does it do? There is a lot of chemistry to it. The reason why they give you zirconia cap, because this zirconia tungstate is the material which is a very good negative thermal expansion material. It's a zero thermal expansion material. So, in fact, these are examples. In other words, if you do a filling of your teeth with this will neither expand or contract with respect to your original part of the tooth, which is inside your filler. Whereas, if you are a little poorer I mean, I would not say that faculty of ISCs are poorer in that sense, but if you are a little poor, then the doctor, the dentist will figure out, do you want a zirconia cap, or you want a cap of something like a little cheaper material? And then, of course, depends. If it is a cheaper material, that thermal expansion coefficient will not match with that of the things. For example, one of the very famous material is called invar. Invar is material. It's called invar because it is a zero thermal expansion material. It is called invar because it is invariant with respect to temperature change. Right? This was one of those materials. So there is a lot of interest in getting negative thermal expansion material. And what we found out that because of the negative thermal expansion, some of this distorted carbon-like system, because of the buckling and anisotropy this, if you heat this carbon network, you will see that they have very large thermal expansion coefficients which are negative. Let me tell you that nature also has its negative thermal expansion material, and you know the molecule of life has a negative thermal expansion coefficient in that temperature range of 0 to 4 degrees centigrade. Of course, as you know, water or ice actually contracts between 0 and 4 degrees centigrade. And because of this, the whole aquatic life in the Arctic and the Antarctic survives because it forms a coating of ice over the water. So it is the same reason. And if you think about more about the structure of ice, I'm sure somebody from condensed matter would have talked about here in a different forum. See, the reason why what happens when you have, because the structure of water, even though water is tetrahedra, those individual tetrahedras between 0 and 4 degrees centigrade, they actually have this crumbling mode. So because of crumbling mode, think of these two tetrahedras which are connected. Now, between 0 and 4, they get populated and they start moving like this. And because of moving like this, you see my end-to-end distances have decreased. So this is why they show negative thermal expansion. But for water, it is in a very small range. But ideally, for materials, if you want to make artificial material, they would have very large window. So we predicted that some of these materials are going to be large. Last year, there was this new material called molybdenum, which was two-dimensional molybdenum. And what we predicted along with our experimental colleagues, we could show that a two-dimensional molybdenum is distorted and puckered, and this is exactly what we found. And this is what we reported, that a two-dimensional molybdenum is puckered and distorted. What do we know? So probably I will stop here just with one more minute. What do we know till now? See, till the best of my knowledge, our knowledge, we have about 4,000 two-dimensional materials known. So if you look at the 4,000 two-dimensional materials known, most of them are puckered. The only ones which are a larger fraction of planar structures are what are called boron, carbon, and nitrogen. In other words, the non-heavy elements which have a large gap are the ones which are more prone to be planar, whereas the heavier ones, as you go down the group, are more distorted. And this easy answer to it lies to the fact that they have electronic states which have come closer to each other, and because of this, there is a mixing between the states. So probably I will stop here. I will stop here with this. This is the periodic table of elements, and the ones which are colored are the ones till now which we know are going to have two-dimensional analogues. You see, there are still a lot of them for which we do not have experimental evidences, and my predictions or our predictions are that particularly for the elements down in the periodic table where the gaps are small, they're all going to be distorted. So we will see how we evolve. At least for the 4,000 compounds or odd compounds which we know, they seem to be valid. And finally, I will stop here by this thing that Daga chain. It is good to be distorted, because only when things get distorted, you get a lot of interesting properties. If they are not distorted, you don't get any interesting properties out of it. And this is also, I would say, this is a kind of a out-of-box thinking, because when people were thinking of two-dimensional material, people were reporting things that were perfectly planar, there is completely no anisotropy and those things. But what we know now, it is important to have a little bit of distortions, controlled distortions, and distortions which get buckling, because that gives to very interesting properties and interesting physics. Unfortunately, I did not have time to talk about here. These distortions, these buckling distortions also lead to some very important phenomena called topological insulators in these systems. And again, because of spin orbit coupling and the anisotropy of the structure, you get very important topological phases, which you will not get if it is perfectly planar. So it is good to be distorted. Dagache. Thank you very much.
Thank you, Ayan. That was fantastic. Questions for Ayan?
See, this is a very good question, and in fact, people ask me this. See, these are spontaneous symmetry breaking. So these are spontaneous symmetry breaking which will happen even at 0 Kelvin.
Yeah. What
But
happens with increased
so obviously, with increase in temperature, we expect the first order correction would be that it will be more distortive. That is for sure. So the things which are otherwise planar at 0 Kelvin would have temperature assisted symmetry breaking. So the 4,000 compounds which we know are distorted probably would become much less. I mean, the planar structures will become even more distorted at high temperature. And by the way, this is known. Even graphene at finite temperature is known to have distortions, not at the local ring level, but at that level of much bigger distortions. So these are finite temperature effects.
Yeah, but for example, when you increase temperature, you'll be exciting thermal phonons. Here you are possibly considering just the zero temperature
Yes,
the
quasi-harmonic
pseudo-point
approximation.
phonon.
Absolutely, quasi-harmonic approximation.
Yeah. So, but what means, do we have a understanding at a theoretical level of what thermal phonons would do?
Yes, for example, one thing is that, by the way, this is known different experiments. People do these experiments for what are called those caloric effects. For example, where people look at the anharmonicity. So when people look at properties for thermal transport, or those effects, so those effects become very important. So in other words, with as you increase the temperature, the harmonic approximation doesn't work anymore. So you have more and more displacive transformations. So you have more and more local disordered structure coming up. So that is the first order correction. I mean, temperature does create more. In fact, temperature can create local orders in between the structures. And of course, as you know, there is no entropy in our calculations. These are zero temperature. So what entropy does to this is something which we have no idea.
Hi. So I have a question regarding the phosphorus thing that you showed. So you mentioned it's like a hilltop,
Yes.
but when you look at the couplings, these are actually like specific modes that you wish to couple, like specific
Yes.
term symbols only have the coupling with them. So what I was wondering is that how are these excited state? They are coupled with respect to the two different modes. And once you start going downhill along certain direction, does your modes change and does that change the coupling further?
Yes, it does. For example, so in other words, this is what I mean. One of the modes will go directly to one structure. That is what we found. The other mode will go to a local intermediate, and then at that intermediate, there will be further vibronic interactions through a different selection rule to go another structure. By the way, this work has been done by, I will tell you, just to be this part of this work was done by Millard Dresselhaus. Millard Dresselhaus had done some of this work based on Raman on some of these systems. Yes, very detailed selection rules for symmetry breaking. Very, very detailed. If you look at her paper, I mean, so beautiful.
So actually,
Very little for us to do in that case, actually.
yeah, so I was just wondering about this other kind of distortion you're talking about, which is not that local, but you have corrugation or don't know what's the right word, where so you are probably thinking of distortions at the level of unit cell, right? You could think of a supercell level distortion.
Yes,
Right.
yes, it does that.
So does that have any application?
It does, but then, I mean, it's like this. I must tell you, this is, I don't know. Do we have something equivalent in Bengali? Those Namutri jokes? We have Gopal Bhar equivalent. No? Yes. So the story goes like this, and I will put myself in that position. See, the question is, somebody lost his golden watch on the road in the night. So that gentleman was asked, then next day morning, I mean, next day, another person, that what are you doing, man? But you know, I lost my golden watch near the riverside. Then why are you looking at here? This is not near the river. No, but this is near the lamppost. Because here there is some light. Let me at least search here. The point is, we have genuine computational limitation of handling very big unit cells. So then of course, if you have very big unit cell, we will have more and more different kind of distortions. So the point is, at least we can handle it at this phase space. So we are looking at this level. But the question is, that does not negate that problem that with higher unit cell, you are right, we will have different modes, more complicated modes.
Yeah, I'm just wondering about any new sort of physics or uses that would have.
Oh, well, we would have more complications, but the point is the physics is the same. The interactions are going to be the same, but the emerging properties may be different. And unfortunately, the state of the art of doing computations, we are limited by what is available. So that light is available only under the lamppost.
Hi. So the vibronic coupling you talked about, it is the linear vibronic coupling, right?
Yes.
It's proportional to the Q term.
Yes.
So but the phonon modes are coupled themselves as well, right?
Yes.
So how do you think about that? Like, let's say if we are in a saddle point and the structure could distort in two different direction, right? But those two directions are also coupled because of their anharmonicity.
Yeah. So here we are not looking at anharmonicity. These are even within the harmonic approximation, you get to see those two minima. As I said, as Pratap was saying, anharmonicity and this becomes anharmonicity become massive when you go to finite temperatures. So those can lead to even more interesting physics. And you are right, we are looking at first order correction.
And the fact
So the question is first order correction to the perturbed wave function, or because the second order correction to the unperturbed wave function do not leads to any instability. It is just the ionic term. I hope you understand that. So there are two terms in second order perturbation theory. Right. The first one is, so coupling between the two ground state using the second order coupling will not lead to any instability. It is the coupling between the ground state and the excited states, the first order coupling matrix. Yes.
And the other thing is like, if you're at a saddle point and you can go two different directions, so is it possible to define the directionality from that?
Well, that is, see, that is the question is, this is like this. You are asking, see, this problem probably cannot be addressed at this level because there's an instability problem. So instability problem is only at the, but of course, finally, by looking at the energy of this, you can probably get an answer. I give you an answer. For the D9 system of a copper, copper 2 plus, hexa copper complexes. So it can undergo two kinds of distortion, Z in or Z out. Ideally, both are possible, but then we know for answer that it Z out are more easy because then that will end up in having two longer bonds and four shorter bonds. So chemistry wise, it is better to have four shorter bonds and two longer bonds rather than to have two shorter bonds and four longer bonds. So that is a kind of indirect explanation. But looking at the instability point, I cannot say which one is going to be. But of course, in principle, yes, by looking at the curvature of it, probably I can say.
So in some cases,
yes.
metals.
Calculations are essentially just energy landscape.
Yes, absolutely.
So can one extend it to free energy landscape?
Pratap, the problem here is there is no way we can take into account entropy here. That is something because see, the good thing is, see, we are looking at spontaneous symmetry breaking. So this is the fact that a silicene will be distorted will be distorted even at 0 Kelvin.
I understand.
So at 0 Kelvin, electronic energy and free energy is the same, right?
Yeah. No, that is right. The reason I'm asking this is that many of these 2D materials, they have entropic phase transitions. They have possibilities of entropic phase transitions. So if one can look at the free energy landscape, then one could see.
Yes, but the way we do it, there is no way we can handle it. So, other than we can do entropy, but that is very rudimentary entropy. Those are
experimentally.
Yes.
Are there, let's say, coupling phase transitions that have been seen or
with temperature?
Yes.
That is something I have not seen. I mean, I have not followed, I would say. I understood your question because then that would be even more interesting.
Okay. Well, if there are no more questions, let's thank Ayan once again for such a simple delivery of such a complex problem. So thank you, Ayan.
Thank you.
And let's move all together for a little bit of snacks and tea with Ayan, and we can have more discussions. Thank you. And there is a public talk after this. Visible and the invisible.